All right, now we're going to continue our study of the central force problem. The last time we left off having reduced all of the equation motions to only one second order differential equation, and then the other two, one of them, the one for the polar angle, we decided was going to be just a constant, and we proved that that was completely plausible, and we did a step-by-step proof of that. We didn't just make this assumption. We actually showed why this is as a constant. And then we have a constant of motion for phi dot, which was a constant of the motion. So that's only a first order differential equation for phi dot, and we're left with this second order differential equation for the r coordinate in a central force problem. And then more importantly, we learned that for all central force problems, you end up with a potential term, which is the angular momentum squared, which was a constant of the motion, over 2 times the reduced mass times r squared. And this appears in all central force problems, and it can be considered its own piece of the potential. So we have a physical potential, which represents the force acting on the particle, which is always the gradient of the physical potential. And in our case, since we've decided it is a central force problem, we've decided that the only functional connection between our coordinate system and the potential is through the variable r. That was sort of an ansatz of our problem. That's an assumption. That's the problem we're trying to solve. And so therefore, this gradient, if you read this in sort of vector terms, the vector force is just going to be the partial derivative with respect to r of u of r, and it will be in the r direction, right, in the r direction. So usually now we, because we're dealing with only one dimension, we can afford to omit this vector terminology altogether and just talk about the force in the direction of r. And so the physical potential is something we need to now insert into the problem, and we're going to insert the appropriate potential for the Kepler problem. Also, just the classical Kepler problem is what we call it, and that potential is going to equal kappa over r. Kappa over r will yield a central force of minus partial by r of kappa over r, which is going to be minus kappa over r squared, which is so the force is minus kappa over r squared, and we can actually I'm sorry. So with kappa over r squared, the force can be positive or negative, meaning it can be repulsive or it can be attractive to the center of our symmetry, depending on the sign of kappa. And I think the standard is, let me see. Well, the standard is if kappa is greater than 0, then, hold on a second, let me see if I can remember this. If kappa is greater than 0, then the force is repulsive. If kappa is less than 0, the force is attractive. So what we now, so our definition of the potential must be U equals kappa over R. And then, oh, there's a minus sign missing here. So the minus, that's a plus, right? And sure enough, if kappa is less than 0, right? If kappa is less than 0, then this whole thing is negative all the time. And if it's negative, that means the force is in the direction of r. It's in the opposite direction of the coordinate r, or of the r unit vector. And the r unit vector is always away from the center of symmetry. If kappa is greater than 0, then the force is repulsive because it's in the direction of r, so it pushes away from the center of symmetry. Okay, so that's our standard, and this is going to be the physical potential that we are going to now put. We're going to take that physical potential, put it in there, and we'll get a differential equation, which we will solve for r as a function of time. Now, before we do this, we probably should spend a moment talking a little bit about the interpretation of this term here. This manifests itself as a force, right? Because the radial coordinate has an acceleration, meaning the radial coordinate of our object moving through space has an acceleration assigned to it, and that acceleration is non-zero even in the absence of a potential. So if we have just like empty space, and we just arbitrarily pick a spot in empty space and call that the center of our coordinate system, and we set UR just to equal 0, there will still be a force acting on R. And let's make sure we understand that. So here is, say, our center of force, and as I've mentioned, UR is going to equal 0 everywhere. Now, I want to imagine that we have a particle in this green particle here, and it has several options of motion. One is it just goes right through the center of the symmetry of the problem. In that case, its angular momentum about the center of symmetry is equal to 0. And then you can imagine the same particle with a slightly with a slight impact parameter. I'll call it an impact parameter. It might not technically be exactly the best thing to call it, but let's say it's got an impact parameter around the center of symmetry. And now it has a value, an angular momentum value, which is slightly greater than 0. And then you can imagine increasingly large impact parameters and increasingly large values of h. I'll call this one h2. And I'll say it's much greater than 0 without being too specific about how to measure things. It's many times greater than h1, let's put it that way. How about, maybe that's the way I should say it. h1 is greater than 0 and h2 is much greater than h1. Some factor of 10 or something. So each of these has a different impact parameter, and you'll notice that this force term here, this guy, this potential, well, I'll call it a force term because once you take its derivative, this potential becomes a force. This force acts on as an accelerating force for the radial coordinate. And what this is telling us is that, as this particle moves, let me draw it in green. As this particle moves along this line, and it's moving uniformly along the line, right? Because we've set u equal to 0. So there's no actual physical forces out there. The only force is this force that's an artifact of the coordinate system we chose. So what does this mean? Well, this means that this radial vector between the center of force and the particle as the particle moves through space, that radial vector's length is changing. Here it's slightly longer than it is here, so obviously its length has changed. Its length has changed from here to here. Well, its length actually may not have changed. It would have gotten a little smaller here, and now it's larger again. So the length here and length here may be the same, but it's gone through this sort of stationary point where the length stops getting shorter and shorter and shorter and starts getting longer and longer and longer. And then the length changes, and then the length changes. And you can imagine if you go way, 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 way out far away, then little bits of motion down this line make for large changes in this radial vector. The point is this is not uniformly changing. It's actually changing with an acceleration. This vector, I'll call it the r vector, this radial vector, has an actual acceleration as it changes through all of these things. And that acceleration that's what this equation means, right? This equation means of h squared over 2 mu r squared, right? When the potential is set to 0, the acceleration of the length, the magnitude of that vector, is driven by this differential equation. So large values of h, and I'm presuming now that the velocity of the particle is the same in all three cases, but so the physics of all three situations is really identical. The particle is just moving straight through space, uniform velocity straight through space. However, the uniform velocity straight through space in this coordinate system is actually accelerated in this r coordinate system. And if you're on this track, r gets shorter and shorter and shorter and shorter and shorter and shorter and longer and longer and longer and longer and longer, but it does so at exactly a uniform and precisely straightforward rate. And, of course, the angular momentum here is 0, h is 0, this side is 0, so mu r double dot is 0, and, of course, you get no force. Now you add a little bit of impact parameter, and sure enough, you can actually get quite a substantial force, because even if you have a small value of h, if r gets totally small relative to h, then you'll have a significant force where this radial vector here tends to start diminishing very rapidly and then growing very rapidly. So the force, this apparent force can get very large right around this area. And also you could have a large fictitious force if you have a very large angular momentum, even if you only have large impact parameters. If it never comes close, but the angular momentum is extremely high, meaning perhaps the particle is moving very quickly along this line, right? So even though it's not coming all that close to the center of symmetry, it's got a relatively large force. So this fictitious force is very interesting, and it's absolutely present only because of our choice of the spherical coordinate system. And it's important to understand that that's what this differential equation is talking about. Okay, so now let's actually go ahead and work on the Kepler problem itself. All right, now I promise we'll get to our ultimate goal, which is a function r of time. But in between, as an intermediate thing, and which is very, very common in this analysis, and which we'll be doing for the Schwarzschild geometry, we will be looking for r as a function of the azimuthal coordinate. And this will give us a shape of the orbit, right? We'll be able to then plot, the azimuth and r for all values of the azimuth. So we'll end up with the shape of the orbit. Now we won't quite know about how quickly it's moving around that orbit right away, but we're going to get the shape first. That's going to be our first goal. And it turns out doing that is much, well, it's arguable about what's easier and what's harder. It depends whether you like complex integrals or not. But so it really, and when I say complex integrals, I'm not sure even what people judge by being complex, right? I mean, it's certainly an integral you can do with tables. So I guess it's just the sequence of things you usually see in textbooks. So usually in textbooks you see the analysis go after r of phi first. So that's what we'll do. So this is the expression that we are going to put on hold for a second, and we're going to back up to the original constant of the motion, where we had not substituted for phi dot squared. You can go back to the previous lecture and find the spot where we actually did that. I will substitute for u, so there's k kappa over r for u. But phi dot squared is still in here. Here's the constant of the motion equation. And you can see that this is entirely equivalent to this. These two are the same. So once we have this is actually a slightly trickier differential equation without the constant of motion to get rid of this phi dot squared. This thing is a bit of a mystery. But we're going to make a couple maneuvers to help us get at this answer. And the first is to understand the nature of this these are time derivatives with respect to time, these dots, right? So the total derivative with respect to time is always going to be the total derivative with respect to phi times the derivative of phi with respect to time. So that's going to equal phi dot d by d phi. So anytime I see a time derivative, I can replace it with phi dot times d d phi, like this. But phi dot, I can use this constant of the motion, and I can say then that this is h over mu r squared d by d phi. So that's the key. Total derivative with respect to time is actually equal to this constant of the motion term which involves the radial component coordinate times the total derivative with respect to the azimuthal variable. And now with that, I can take this expression, and everywhere I see a dot, I can insert this guy, and I can convert this equation from an equation with the independent variable is time to an equation where the independent variable is phi. And notice I could only do that because I had a constant of the motion. You can't emphasize how important these constants of the motion are. So let's do that substitution. So I think the first thing I'll do is I'll explicitly put in the time derivative term. Notice these are total derivatives. These aren't partial derivatives. These are ordinary derivatives. And I also substituted for phi dot squared using the constants of the motion to eliminate that here. And then this is the potential. Now I will substitute, now I'll do the substitution. Every time I say d by dt, I will replace it with this d by d phi and this factor here. And notice this is a second derivative, so I've got to be a little bit circumspect on about how to do that. And I just noticed, as usual, this should be this term here. I forgot to square it. Right, would be mu squared r to the fourth, right? Because I'm looking for phi squared, right? Phi squared. So it's h squared over mu squared r to the fourth. That phi squared will replace this phi squared here, right there. So I need h squared mu squared r to the fourth. Okay, so when you expand this and you replace these d by dt's, you, well, the first thing I did is I multiplied this out to get h squared over mu r cubed. Then this stays the same. Then the first dt against the first derivative attacking dr replaced with this gives me dr d phi with h mu r squared, which is not a function of which we treat as an independent variable, so we pull that one term of that out, and then but we have to leave the r squared behind because r is a function of phi, right? So so that's a good point. So r is a function of phi. So when I bring this in here, I take dr d phi. I have to leave this r behind because I'm going to hit it with another d by d phi. So we have to expand this guy out. But this d by d phi comes with its own h over r squared, which does come out in front. It's not to the right of the differential operator here. It's not, this differential operator doesn't act on its own r, so that r comes out in front. So you end up with h over mu, so you only have an r squared because you're only getting the r squared from one of the d by d phi's, the second d by d phi. So that gives you the h squared, that gives you the h over r squared. The second h comes from the first d by d phi, which is a constant, so it comes out. One of the mu's comes out. Both of the mu's come out front, so that gives you the mu squared, and then this mu is the mu that's part of the force term. Phew. And then this, of course, is the actual force, so that we've already been talking about. It ends up being essentially the gradient of that potential. And that needs to be a force. This is a mass times an acceleration. This is a force. This is a force, of course, as well. So everything works out. So this is our new expression. Now the solution, the independent variable is phi, so now the solution is r of phi, right? And the next step is to cancel and simplify a bit. So let's do that. I think what will happen here is a lot of these h squares over mu r's they'll go away. So let's just clean it up. And if I did everything correctly, this is the simplified version of it. This is essentially the same thing with a bunch of these h mu's and r squareds kind of pushed over to this side. Now notice this side still has a derivative with respect to r. I could take that right now. I could replace that right now with minus kappa over r squared. The minus would cancel minus, so it would be plus, and then I guess this would be mu over h squared, kappa over r squared. So we could make that replacement right now if we wanted to. There's really no reason not to. It's still a perfectly fine differential equation for r of phi. So now what is our next step? Our next step is to start attacking this as a mathematical problem. Now we have a differential equation for r of phi, and it's no longer a physical insight problem. It is now the physics has given us, it's this class, this is the way physics works. The physics has given us a model of the situation. The model is a mathematical model, which almost always means we're dealing with a differential equation of some sort. And now we are faced with a simple differential equation. So now we kind of turn this over to the mathematicians who've studied such things, and we find the answer to this differential equation. And mathematicians have looked at equations like this for a long time, and so they have all kinds of insights about how to simplify them into forms that are easily understood. And that's our next step. So what we're going to do is make the mathematical substitution that has been tried and true for this problem over the years. And don't be worried if there was a period where I was thinking, holy crap, I wouldn't have thought to make that substitution. Therefore, I couldn't have solved this thing all by myself in a naked and empty, a universe completely devoid of other people teaching me how to do this, because I'm not smart enough to realize that, hey, the following substitution, which this is going to be a little u, right? Little u. The following substitution simplifies this differential equation. Because I had to be told that instead of figuring it out, that's okay, right? I mean, the guys who worked on this spent their whole lives working on these things, and they taught us what they learned, and now it's our obligation to learn it and recognize it and appreciate it, but we'll be inventing other things, right? We're going to spend our time farther down the road, right? That's how science is supposed to work. So I guess the way I'm saying is don't feel intimidated by differential equations. Don't feel intimidated by any mathematical thing that looks really, really hard because you feel like you couldn't have invented it from scratch. Just learn it, work the problems, be excited about the discovery, because that never wears off. Learning things for the first time is always a real thrill. And just keep going. Now, in this case, we're going to make the substitution. The u is equal to 1 over r. And that will convert this differential equation into something a lot easier to understand. So I'm working on this replacement. This guy here becomes u squared. The d phi stays the same. The 1 over r squared becomes u squared. The dr has to be converted to du. Well, du is minus 1 over r squared dr down here now, right? And that's minus 1 over u squared dr, which tells us that dr is minus 1 over u squared du, and that substitution went right there, all right? And then that leaves us with a du d phi. Then this r cubed becomes minus 1 over u cubed, and then we have mu h, and then this I'm leaving alone, right? I'm leaving this the same, even though it's derivative with respect to r, because ultimately we're just going to come up with a function of r on the right side once we execute this derivative, which, like I said, we could do right now. We could make that substitution right now. And we will in a moment. I just wanted to take it a little bit slower. But this now, if I go ahead, this guy will actually cancel. There'll be a minus sign out front. Then I divide everything by u squared, and I end up with a I divide everything by minus u squared, so I end up with a plus u here, and the minus goes away, and I have a u squared in the denominator there. So this should end up being du squared d phi squared plus u equals plus mu u squared h squared times d by dr of the potential u, which we know is going to be kappa over r. And this is now a very different looking differential equation than this was, right? And now we are solving, however, for u of phi. right? U of phi is the answer to this differential equation. And U of phi, right, gives us R will equal 1 over U of phi, right? So we can immediately get R back once we solve for U. It's really not a problem. We just inverse this substitution. So, you may have seen this problem already in your first version of classical mechanics, or this kind of substitution also happens in the central force problem in quantum mechanics. It's, you've seen the central force problem several different places probably. You probably saw it in Rutherford scattering with a kappa that was repulsive. You probably saw it in quantum mechanics where you just did the central force problem for the hydrogen atom. And this is like the simplest version of the central force problem. But sometimes it's not covered in all classical mechanics classes. Okay, so this is our differential equation. So our next step is to take this expression and actually go ahead and execute the right-hand side here. And here's our start, right? We take that derivative, that's this derivative right here. We take this derivative of kappa over r, which is our Kepler potential with respect to r, and we end up with this expression, minus kappa over r squared. R squared, using little u, equals 1 over r. I hope I'm not confusing things too much. Capital U is the physical potential. This is the physical potential. So when I write capital U, of r, I'm talking about the physical potential. This little u is just a very, very common in many textbooks substitution for this 1 over r. I just see u used all the time. So this is a little u used in a different context. So we can make the substitution for this 1 over r squared, which would now become little u squared. And so we end up with little u squared from here to, that's the denominator is this little u squared. The little u squared from that substitution goes in the numerator, and this stuff all cancels. I should put the cancellation in red. And so you end up with a clean differential equation that looks like that, right? And that's our central force problem. But look at that differential equation. That differential equation is completely well known to us. It shouldn't be any trouble to solve that. That's just a second order, because of the second derivative, linear, ordinary, because there's no partial derivative, so it's ordinary differential equation. And we know the solution to this thing. You should be able to literally write down the solution to this. There are very few things I insist that we all be able to do from memory, right? Integrations and taking integrals and derivatives of like elementary sines and cosines. That's something you need to memorize. There's a certain collection, a second-order linear differential equations, second-order ordinary linear differential equations, you should have pretty quickly in your mind a way of immediately getting at the solution just by writing it down. On the other hand, I never pass up an opportunity to review the most elementary things. In this case, the characteristic equation for this differential equation is r squared plus 1 equals 0 with two roots plus minus I, which implies a solution of a to the e ix plus b to the e minus ix, which we know, because we remember, that this implies a solution a prime cosine, when I say x, I should say phi, right? Phi. Cosine phi plus b prime sine phi, right? Which I also know can be converted to a, I guess, double prime cosine phi minus phi 0. So in other words, what I've done is, we get two arbitrary constants. We know we can rearrange these exponentials into trigonometric functions using the legendary Euler relations one way or another. We get two new constants. And those two new constants can also be combined using various trigonometric identities to a constant magnitude, amplitude, and phase angle, where now these are going to help characterize an orbit. So we know that u of phi has this form, and the phi 0 just sort of specifies the initial angle of the orbit, sort of the initial conditions of where the problem starts, and this has to do with the initial the initial magnitude of this function. So we know that we got a solution that looks like this thing. But then we have a particular solution also, because remember we have this force here, right? So there's an inhomogeneous term, but that inhomogeneous term, in this case, we know, because we remember from our elementary differential equations, is just the function u equals minus mu kappa over h squared. It's a constant, right? If mu equals that, it's a constant, so the second derivative is 0, so this term goes away, and then you just have that equals that, right? So that's easy. So the total solution is going to be u of phi is a double prime cosine. You know what, I'm going to get rid of the double prime, just because I only used it to distinguish these from each other, but now I'm just going to rename it a cosine phi minus phi 0 let's see, I guess the way I should do this is minus mu kappa over h squared, right? And then I'll make it even simpler by pulling out a minus mu kappa over h squared, right? And I'll write it as, if I pull out a minus u kappa over h squared, I'll call this, then I can define the inside, 1 minus e cosine phi minus phi 0. So I'm basically using this extraction of mu kappa over h squared to, and this is an arbitrary constant here, an arbitrary constant of the differential equation. So what gets left behind is still an arbitrary constant, but I'm going to give that constant a name. I'm going to call it E, which is the eccentricity of the orbit. And then from this, we just come up with R of phi is 1 over u of phi, which is minus h squared over mu kappa 1 over 1 minus e cosine phi minus phi 0, like this. So when we look at this thing, what do we got? Well, kappa is known, right? Presumably the physical potential U of R, which was kappa over R, so kappa is a given. Kappa is a given. It's basically the force constant for this Kepler potential. So we know what kappa is. So the only undetermined things is phi 0, right? And E. Now phi 0 clearly has to do with where this orbit starts. So we can actually arbitrarily take phi 0 to equal 0, which means that so we're now getting a function that when we input phi into the function, when phi is 0, we're assuming that we're talking about measurements off of the azimuthal axis, right? So here's the off of the azimuthal measurement here. When we put in phi 0, we're actually starting along this axis. It's really a very arbitrary thing. It's not a problem at all to just call phi 0 equal to 0. So that leaves us with one unknown constant, and we have to sort of understand that thing. So putting aside how to determine that constant for a moment, what do we know about this? Well, now again, we have to lean on our familiarity with mathematics, and we say, well, wait a minute, this is R of phi. That form we know is, from classical mathematics, a conic section. A conic section where E is the eccentricity of the particular conic section. And so once we understand that, everything else flows from it. And we can extract all of our geometry from that. So you may remember that in a conic section, we have a whole bunch of really useful expressions. First of all, the formula for a general conic section is R equals some constant S over 1 minus E cosine phi. That's your standard conic section formula. Now, these things, when you study conic sections, everybody kind of runs through these things with slightly different definitions. S is called the semilattice rectum, but the semilattice rectum, S equals the eccentricity times something called P, where P is the focal parameter, right? Focal parameter. And this is the semilattice rectum, right? I'm not going to go into all of this in great, super crazy detail right now, but because it's so easy to read on. I mean, this is just elementary geometry, but I want you to make the connection between all of these things. So R could be EP times 1 minus E cosine phi, right? That's another way of seeing R. But we also know from this that the apoapsis of the orbit, the smallest value of R, is EP over 1 minus epsilon, 1 minus the eccentricity. And, I'm sorry, the apoapsis, that's the farthest, right? That's the farthest. And the periapsis, which is the closest, is EP over 1 plus the eccentricity, right? So we know those facts right away. And that's all from an analysis of conic sections. So we want to use that and some physics to figure out what is the eccentricity of our problem, right? Because our problem, that all depends on initial conditions. That's what physics is. So we need to figure out E for our problem. So how are we going to do that? All right, I can't resist doing a quick conic section review. So let me make this sort of as smooth and as quickly as I can. You can skip this part if you understand your conic sections really well. All right, so the basic premise here is that we have a line in space that we call the directrix, right? That's one line, arbitrary line on the plane. And then we have a point that's not on that line that we call the focus. And what we're going to do is I'm going to just draw a perpendicular from the focus to this line, and that is going to establish somewhat of a coordinate system for us right now. But the directrix is the key here. Well, the directrix and the focus are the key to the conic section. So if I take a point out here in the plane, say right there, I can form two distances right away. One is the distance to the directrix, dd, and one is the distance to the focus, df. Now now there will be a ratio of these two distances, and the way we write this is that E, this number E, the eccentricity of the conic section, times the distance to the directrix equals the distance to the focus. So right here in this particular picture, E is approximately equal to 1. The way I've drawn it here, this D, let's imagine for a moment it's equal to 1. Now I take all of the points, I set E equal to 1, and I'm going to take all the points that are an equal distance from the line as they are from the focus, where the ratio of those two distances is always equal to 1. The distance itself can change, right? df doesn't have to be constant. If it was, we'd just have sort of a circle, and then if we had some circle, clearly dd would be changing a lot while df is constant. So the two change together. The point is they change at the same rate with the constant ratio of e. I guess another way to write it is that the distance to the focus divided by the distance to the directrix is always equal to a constant, and that constant is the eccentricity. So if we set the eccentricity equal to 1, we end up with, we look for all the points where that's true. And if we do that, we end up with a set of points that looks like a parabola. And I'll just draw it approximately this way. I'm not sure that this is a perfect parabola, but if it is, then we know that, say, this distance here and this distance here will always be the same. And that's a parabola is defined as this kind of curve where e equals 1. And all parabolas that we've ever worked with in algebra can be reinterpreted in this way. Now we can do the same analysis for the conic section of the ellipse. There's two directrixes for the ellipse. And the principle is, though, identical. Every point on an ellipse, or an ellipse is the locus of all the points. You know, for example, I'll take a couple here, like this, where the distance from the point to the directrix, which is d directrix and d focus, E times d directrix equals d focus. That formula is the same for all conic sections. Ellipses, hyperbolas, and parabolas. Parabola E is 1, so you can just write dd equals df. But for the others, you'll have this number e. But in this case, e is less than 1. It's greater than 0, but it's less than 1, and you get an ellipse. And so that's how you define the ellipse as a conic section. And a hyperbola is the same thing with e greater than 1. So e is greater than 1 for a hyperbola. The key dimensions for an ellipse is actually the one we're probably most interested in right now, but the key dimensions for an ellipse are the following dimensions. This line here, a perpendicular through the focus, parallel to the directrix, a line that's parallel to the directrix and goes through the focus, will intersect the conic section at 2 points. The length of that line is L, and that is called the latus rectum. The latus rectum. And half of that distance is called S, and that is the semi-latus rectum. And then the distance between the focus and the directrix, this distance he would call P, that is the focal parameter. And for an ellipse, well, I think for all conic sections actually, the eccentricity, this value of E, this special ratio, multiplied by the focal parameter equals the semilatus rectum. I think S is a bad choice for me to use for semilatus rectum. I think one of the books I use actually uses S for the focal parameter and something else for the semilatus rectum. But or it doesn't even name these things. But Chandrasekhar's book on general relativity, the one about the mathematical theories of black holes, it heavily uses all of this conic section language. The specific ones I've introduced here: semilatus rectum, the focal parameter, and the eccentricity. So, and this can be defined just as well for the hyperbola, where here I've done it, just sort of caught it up real quick. The two directrices are here on the inside, and now E is greater than 1, so this distance here is a bit shorter than this distance here, right? It's going to be shorter by a factor of E, which is greater than 1. And you end up with two foci, just like in the ellipse, but you kind of have this sort of inverted shape. Understanding the hyperbola is a really, really good thing, because special relativity has a lot of hyperbola-related mathematics, if you don't know already, and in particular, this whole concept of the rapidity, which is a very convenient concept in special relativity. Understanding hyperbolas is real important. But this will also have a semilatus rectum, just like that, or that would be a semilatus rectum and a lattice rectum, and a focal parameter would be right here, that would be P. And so with the ellipse, you also have a formula for this distance here, which is called the periapsis, and the distance to that closest point from the focus to the closest point is, let's see, I know it's 1 plus epsilon in the denominator. I know there's not epsilon, 1 plus the eccentricity in the denominator. The eccentricity is in the numerator, but it's also times the focal parameter. And the distance to the far point, which is called the apoapsis, that formula is very similar. It's the eccentricity times the focal parameter times 1 minus E. So the denominator shrinks, and of course RA is bigger than RP. So that's true only for, I think these formulas are only true for this case. Obviously, in the case of the hyperbola, there's no apoapsis really, it's infinity, right? So those are the key points about the ellipse and the hyperbola that you need to know. So now we go back to our ultimate expression here. We calculated r of phi, we got this expression here, and we know that this is in exactly the form of a conic section if we choose the semilattice rectum S, which is the eccentricity times the focal parameter, as we just sort of went through. And if we choose it to be commensurate with this here, with this constant here. So we would have to write down an expression that connects S to that constant. So we are now looking at the two expressions we have for the conic section. One is the mathematical expression, and this mathematical, sometimes you'll see a plus here, by the way. This will end up looking like this, and that purely has to do with the way everything is oriented, the way the directrix is oriented relative to the focus. So just keep alert to, like, if you go all the way back to the parabola, you could make it horizontal directrix. You could have the directrix, on this side, and the parabola going like that. So you can have a couple different orientations, but our orientation is the one that ends up with a minus sign right here. And then we have the physics expression for the shape of the orbit that was derived through the Lagrangian analysis. And so to equate these two, we would have to write E, the eccentricity, times the focal parameter equals minus h squared over mu kappa. Now the right-hand side we can calculate because we from initial conditions we know h. This kappa is just related to the strength of the potential, which is a statement of the problem, and mu is the reduced mass of the system, which is also a statement of the problem. So this is known. We're trying to find the eccentricity, but this doesn't really help us too much because we also need to know this other parameter, this focal parameter. So we can't really solve for the eccentricity here. So what do we do? Well, we are now going to appeal to physics again because we've only used one constant of the motion in this story, and that is the angular momentum. We still have the total energy to work with. So let's have a look at that. We remember that the Lagrangian of the system, the Lagrangian, was a function of our generalized coordinates. We had r, theta, phi, r dot, theta dot, phi dot, the generalized coordinates and the velocity. And time was allowed in there, but it wasn't actually part of the expression. When that is the case, then we know that when time is not part of the Lagrangian explicitly, it's always sort of in there because, these are derivatives with respect to time. But when time is not explicitly part of the Lagrangian, you may remember from the earlier lectures, that means that the total energy, that means that the kinetic energy, which we call T, plus the potential energy, which we call V, those two together are a constant of the motion. Now generally we call that the total energy, and in this case it is the total energy. There is some possibility that T plus V will be a constant of the motion, but it won't actually represent the total energy. That circumstance happens, I think we discussed this in our previous lecture, but that circumstance would happen if I took these generalized coordinates, r, theta, and phi, and I related them to some inertial coordinates, say x, y, z, r of x, y, z. If these are inertial coordinates, x, y, z, and the relationship between, if the relationship between the generalized coordinates and inertial coordinates includes time explicitly, then it's still true that t plus v is a constant of the motion, but it doesn't really represent the total energy. So that's a little obscure point. But in this case, that's not the case, right? The relationship between the radial coordinate and, say, an inertial coordinate of x, y, and z, it's completely time independent, likewise theta and likewise phi. Meaning if I know x, y, and z, I know phi. If I know x, y, and z, I know theta. If I know x, y, and z, I know r. And I don't need to know t. Those relationships are true for all time. Okay, so, but I haven't solved for that constant of the motion yet. So what about that constant of the motion? Well, this is that energy, right? This is the kinetic energy term. It's all this r dot squared term. And this is the potential energy term, where this actually is the effective potential, right? So the full effective potential shows up there. And this is the, and remember, that full effective potential, it kind of gobbled up the phi dot squared term that would have been kinetic energy, right? So, or in fact, you can actually think of that as maybe it's actually smarter to just think of that as the kinetic energy term for phi dot, right? Because it's the same thing, right? So the point is, though, this is the total energy. Whether you consider this term as a kinetic term or as a potential term, you're still adding things together. And once you do that, we know it's a constant, right? We know that this is a constant, and we know that from our principles of Lagrangian mechanics because of the nature of the Lagrangian that is missing this time dependence. So we know it's a constant. So if we can calculate it for one place in the orbit, a convenient place in the orbit that might make it easy to calculate, then we'll know that number for good. So what we're doing is we're going to say, okay, let's think of this as an elliptical orbit. It really doesn't matter what orbit it is, but there is this point where the orbit is very close to the focus, and here's this point where the orbit is very far away. That's the apoapsis, and this is the periapsis, right? So at those 2 points, r dot equals 0. So if we calculate this at one of those 2 points, r dot goes away and this term is gone. So we would just have to substitute RA here and RA there, and we get E. So let's do that. So our first step is to substitute RA in the denominator here and here. By the way, this C is our parameter for is our potential parameters. That's we're actually using K. I have C written down in my notes, but K is what we're using here. So we substitute for RA. Now we know that RA is EP times 1 over 1 minus E, and we've already decided that EP was equal to minus h squared over mu K. So it's minus h squared over mu K 1 minus E, like that. So I can substitute minus h squared over mu K for these two EPs. And that gives us this expression here, where I'm just all I'm doing here is I'm substituting in for EP, right? EP was minus h bar squared over mu K. Because we're squaring it, that sign's not going to matter. Then this sign will cancel that sign and turn it into, wait a minute, there's a plus sign here. This should be a plus sign. So there's a plus sign there, and then you'll end up with a minus sign in that term. And what does it look like when you simplify? And the first simplification of just canceling terms gives us this expression for E. Notice that we have known constant, known constant, known constant, unknown, and all this is known, and that's unknown, right? So what we're going to ultimately get here is an expression for the eccentricity in terms of the energy. The energy is known also, just like the angular momentum is known. It's a stipulation of the initial conditions of the problem. It's entirely derivable from, if I'm giving a particle and its initial speed and direction, I can calculate this total energy, and I know everything else. If I know its mass, and since I know its direction, I can calculate this angular momentum. So the initial conditions give me everything here except E, so I'm going to get an expression for the eccentricity in terms of all known quantities. And so the next step is to basically solve for E. And this is the equation that'll do it for us. We just cancel out this term. Well, we might multiply through by the reciprocal of this term and bring E to the other side, and we have a quadratic equation for 1 minus E. When I say E, I'm talking about the eccentricity. Obviously, the energy is capital E. But 1 minus the eccentricity is now the, you can think of this as a quadratic equation for 1 minus E. And so the solution to that thing, we just run it through the quadratic equation, make sure we got this right. It's minus B, so that's the plus 2, plus or minus the square root of B squared, which is 4, minus, I worked this out, so it's minus 4AC. A is 1, so it's minus 4. C is negative, so that minus becomes a plus, and this is C, 2EH squared over mu K, over 2, and that reduces to 1 plus or minus the square root of 1 plus 2E h squared over mu kappa. Make a big square root there. And therefore, with that, you subtract 1 from both sides. What do we do? We end up with E equals square root of 1 plus 2E h squared over mu kappa. I guess what we're going to do is we're going to keep the minus 1, the negative 1. And there you have it. There you have the eccentricity as a function of everything that's known about the problem. The angular momentum, the initial energy, the initial energy, which is constant, the initial angular momentum, which is constant, the strength of the potential, which is kappa, and mu, the reduced mass. And so with that, now we have solved this problem, right? We now have solved we have a total expression for the radial motion as a function of the initial angle. I guess to clean that ultimately up, we should write it down. And there we have it. That is our expression of the shape of the orbit in polar coordinates. Now, we still have not found r as a function of time. And that's what we're going to do in our next lesson, which I'm going to go ahead and work on immediately. So think about this, but this guy is actually easier to get to start on, but the problem is basically a problem of integration. But I do want to work through the integration because most books don't, and I always like to take a chance to learn something or to review something. So next time we will now find r as a function of time. Okay, see you then.